which one? So this fold in half is what? It is not one-to-one, nor onto. But you can think of a fold that is not one-to-one, but onto. If you fold it like this, it's still a fold, so it's not one-to-one, but it is onto. Okay, so one failure will produce one failure to be one of both. Then we'll have a function that's not invertible. Okay, so these are the transformations of how we think of these transformations. The algebra is still to come, even though you can see example right there on the right. So early on you can see the algebra behind these transformations. And then okay, so more algebra. Once again, we start with a function over there, happens to be linear. We write it as a relation. See that is on the right is a relation. Y equals 3x minus 7. It just happens to be y is isolated and expressed in terms of x, but that doesn't make any difference because we can solve for x, and then suddenly we have we arrive to the opposite, x in terms of y. Same relation, just chosen the rows have been flipped. Okay, so it might be more complicated whenever a function is more complicated. X squared, you run into the problem with the domain versus range. Okay, so function is invertible. We know that for the function to be a one-to-one, it has to satisfy. Remember the horizontal line test. So that all of that will come into play. The simplest class of functions that we have solved once and for all in terms of inverses is linear functions. We take them through this algebra. It takes exactly one line. And it's done. So whatever I just did a minute ago with a function that is one particular linear function, and now we have all the linear functions at once. Okay, so and as you can see, slope becomes the reciprocal, including negative ones too. By the way, it's probably worthwhile to have a picture that shows that how these are two positive slopes. What if the slopes are negative? The same story, obviously also reciprocal, but instead of, so if you had negative, say, negative 1/2, this is the slope of negative 1/2, a slope of negative 1/2, like this, negative 1/2. So its inverse will have slope of what? What? No, negative 2. Right. So like this. Okay, so the idea is, and that's what we are getting to, is the relation between the two graphs. The relation comes from a flip that came up some time ago, a new kind of flip. So we had flips. Remember, we had a flip about the two axes. This is also a flip. If you look at these straight lines, it's also a flip, but it is a flip about the diagonal. This diagonal, y equal x, and as you can see, that this is the symmetry. So imagine that instead of having your piece of paper and flipping it vertically or horizontally, which we have done so many times, imagine that you grab that piece of paper by, okay, like this one, like this. So we did this, and we did that. Okay, now imagine that you do this. Okay, and then, okay? Well, certainly I guess that's what we did actually last time. So the Paint and other programs do that fairly easily, except you have to usually carry out two operations in a row. Remember, flip and rotation, right? That's what we did in the end of the last class. Okay, so the second picture on the left, it's also there is a flip. It's still about the same axis. Let me show you that what sometimes happens to be a confusing part. It appears that these two lines have symmetry about this diagonal. Oops. Appears to be a symmetry between these two, which is true, but I still insist that this is the actual axis. So we're doing this flip, even though we could have done the other one. It's just a coincidence, no more than that. So we pick this one, y equal x, as our axis of symmetry. So it's a mirror image, except the mirror, just like before, except the mirror is put in a diagonal way. Okay, so that is a simple example. The more complex functions will also appear. But before we go there, this is the algebra. Is worthwhile. Why it is such an important topic? Because how many algebraic operations appear as inverses from the very beginning. It might not be entirely obvious, but when you are dealing with algebra and you develop new algebra as needed, you don't do anything that you don't have to do. So you're doing some business as usual, and you are adding money or you are adding sheep, doesn't matter. At some point, you might have to do subtracting. So you don't know that, you don't have that concept yet. But you know that if your business partner is supposed to have extra 3 sheep, then and you're supposed to give it to him, then what is happening to the number of sheep that you have? You subtract. Okay, so that's the opposite. The opposite of adding and subtracting there is this new operation that you have known before. Now is subtracting. So you have known addition for a long time, but now you have to learn how to subtract. In a way, you will make up that new operation. Then you come up with a name for it, but it's just inevitable. And the same thing if you have been doing multiple multiplication, say maybe interest rate. So you pay 10% a year, then that's multiplication, literally. But then if you want to go backwards and you want to know what if instead of growth you have decline, then you might, or rather better yet, if I know how much money I have today, how much money did I have a year ago? Instead of multiplying by 1.1, yes, you divide by 1.1. So that's how we discover division. And on and on, wherever you see multiplication, every time you sort of problem that you might be dealing with might be sort of reverse in problem. So you keep asking questions and then answering them, but at some point you have the answer, you don't have the question. So like it's been usually, if I have $1,000 now, and in 1 year I will have how much? The answer is at 10% you have $1,100, right? But what if today I have $1,200? How much did I have a year ago? You have to divide. Okay, so that's the idea of inverse functions, and that it is very profound. Squaring. So how does a square come up in life? So we have 2x2 tail, tile. I'm sorry, and then so that's how you know it's a 4 square feet tile. Okay, but what if I have a tile which is 5 square feet? What is the side of the tile? And the answer is square root of 5. Okay, so that you come up with a new operation in a very simple way. That's you make it up. It is the inverse of squaring. Division. What's division? It's the inverse of multiplication, and similarly with addition. And then every time you see any operation, either an exponential function or it is trig functions, always there might be a question asked that is the opposite of what you have. So direct computation, and then you know the answer, or you know the answer, you want to find out where it came from. If you go backwards, that's the inverse. Okay, so these are the simplest operations, so as we progress, we will add to this list more and more functions, and all of them will be one way or another have inverses. So the stumbling problem is still the same as the whether the function is one-to-one onto, but we already know how to handle that problem. We did it with the that is right here. You see here what we do with the x squared in order to make that function invertible. Okay, so it is not invertible to begin with. Generally, as stated, it's not invertible. It's not invertible, so there is no inverse. So what do? You limit the domain and the codomain in order to make it invertible. Okay, so the same applies to fourth degree power, and so if you want its inverse, instead of square root, you have fourth degree root. Okay, and then once again you have to do the cutting of the domain and codomain. Not such a problem with the cubic because it is one-to-one onto. Okay, so so that is what has happened. Once again, the relation, I try to make that picture in the middle that indicates the relation is two-way, from x to y and from y to x. You can use the same picture as far as the relation is concerned, but if you want a function, then you will have to flip. I would, if I were you, I would keep the names of the variables intact. So if my variables were x and y, and y was equal to x squared, let's just keep the same names. And I have, as you can see, the function will be over here. It is x is equal to square root of y. Okay. So that way, so how does that help? For one, you know how to handle composition, right? Because now if I have what is it? Y is equal to x squared, and I have x is equal to square root of y. Okay, so to confirm that this is they are inverses of each other, substitute. Substitute as it is where is our interpretation of the inverses right here as the composition of the function with its inverse gives you the same element. It is circular, fully circular diagram. Okay, so and that's why when you keep the variables intact, you know where to substitute. You substitute y to replace y, and you replace x with x. Two ways to do it, and in either case, you end up with what you want. So just let's substitute. Number one, I substitute. What do I have? I have x is equal to square root of y, which is also equal to square root of x squared, which is x. As long as x is larger than or equal to 0, this is true. For the opposite substitution, we have y is equal to x squared, and it is equal to square root of y squared, and it is equal to y. Okay? As you can see, the beginning and the end is the same. You can see it algebraically. You can see it graphically. Okay, so the flip you can see here, x squared on the left, the flip of the graph. You can see the square on the left, and you can see the square root on the right. So it is a good exercise, and it is a typical problem for any kind of test, is to ask you to plot the graph of the inverse. Okay, so we already did it. Let me find that picture that we did last time. What was it?